There are three sections of the syllabus. Usually we divide it in physical, inorganic, organic. We're done with the physical, and then we have now inorganic chemistry. And inorganic chemistry is mainly things to memorize. It's very fascinating because you see these patterns and things that are completely independent of each other and probably don't really seem to have any connection with each other. But there's slight differences that create so many similarities, and of course, a large number of differences between different elements. We will mainly focus on periodic table for this, the inorganic chemistry, and we will try to learn how different elements and their compounds behave. or sorry, or if there is some similarity, some pattern in there somewhere. Now, the general structure of the periodic table, we know there are 18 groups. So there's this website, ptable.com. That's a pretty useful one. So there are 18 groups of the periodic table. So now, since we are in A levels, we are not saying that there's transition metals that don't really have a group. We know that transition metals start at group number 3, and at group number 12, there are some of them that are not typical transition metals, but regardless, we do have transition metals. There's also a staircase in the periodic table. So metals that are on the staircase or below that, we usually call them post-transition metals. So there's the transition metals in the middle, and there's the post-transition metals. And after that, you have non-metals. There are a few groups that you're already familiar with, like, alkali metals, alkaline earth metals, halogens, noble gases. And that's fine. That's all good. We also know that there are periods in the periodic table, the horizontal rows, we call them period. And there are two that are usually broken down, element number 57 to element 71, and then element number 89 to element 103. All of these are broken down as part of the longer periodic table, and they're usually written at the bottom. We call them lanthanides and actinides. For A levels, all you need to know is that lanthanides and actinides are usually, many of them are radioactive, and element number 92, uranium, that's the largest atom that is naturally occurring. Any element beyond that is the one that we make in the lab, which is one reason they don't have relative atomic mass. If you notice in the periodic table, elements beyond 92 don't have any fixed relative atomic mass. So can you think of a reason why that is? Why don't they have relative atomic mass? It's really simple. It comes from the definition of relative atomic mass. We say the relative atomic mass is the average mass of all naturally occurring isotopes. Naturally occurring isotopes. These elements don't exist naturally. So no wonder they don't have any naturally occurring isotopes, which is why they don't have any relative atomic mass. Now, the form of periodic table that you are familiar with from O levels was the one that said element number 1, 2, and 3 was the one with aluminium. But now we're saying it's not 3, it's 13, and it's not 7, it's 17. Okay, so just add 10 because the 10 columns of the transition metals take that place. So that's how you get the structure. Now there are patterns across the whole periodic table, and that pattern is called periodicity. Okay, so what's periodicity? It is the patterns that we see in the periodic table. Now, we will talk about some patterns that we have already seen. Like, we've already talked about patterns in atomic radius, but what exactly is atomic radius and how do we figure this out? Now, for that, what we need to remember is that an atom doesn't really have rigid boundaries. An atom is usually like a cloud. So there is the nucleus in the middle. Let's say this is element A. So it has nucleus in the middle, and there is some area around it, usually in circular fashion, that we say that acts as its atom. Now, we might want to measure the radius by saying, okay, this is the radius. But the thing is, how do you know where the edge is? How do you know where to stop? We don't know. That is why usually we don't measure the radius like this. We can't. So we look at molecules and they make things much easier for us. So let's suppose there's this molecule of A bonding with another A. So now what we're going to do is we're going to figure out the distance from one nucleus to another. And that's easy to figure out because nucleus is heavy. When you do X-ray crystallography on it, nucleus does shine up. So you can clearly see where the nucleus is. So find the straight distance, the smallest distance between the two nucleuses. Break it into 2 and you have the radius. And that is one way of looking at the radius. In metallic lattice, we do crystallography again. We do see nucleuses. We divide the distance between two nucleuses to find that. Okay, so that's pretty simple. You can find the atomic nucleus based on this. There are also ions, and for ions, we might want to figure out the electronic configuration and then figure out what the ion is. So उसमें भी हमें crystal को देखना पड़ता है कि वो किस तरह से. Okay, so that's the atomic radius. We usually take the covalent radius. This thing is called covalent radius because they have bonded together covalently, and we are just finding the radius of the two um, atoms from the single covalent radius that we just found. Now, there are some other patterns there, and I'm going to focus on period 3 for now. Period 3 is the one with sodium. So there's sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. These are the ones that I'm going to focus on just above the transition metal row. The radiuses go like this. This is 0.179, 157. I'll just take the values from your book. So if yeah, this is the one. Yep. So these are the values from your book. Do you see a pattern here? Number one, tell me, why don't they show us the covalent radius of argon? Why is the value not given? It's simple. Argon does not form covalent molecules. That's it. If you look at the atomic structure, it is decreasing, right? There is a clear pattern there. Atomic radius is decreasing. The atom is becoming smaller and smaller and smaller. And we know this. We know this already. We know that sodium has 11 protons and chlorine has 17 protons. But they're in the same period. They have the same third shell. So there's no extra shielding that's coming in. But the protons are increasing. So the same third shell is being pulled towards the center. More in chlorine, less in sodium. That is why the atomic size decreases across a period. We know that. Okay. And why is that? The reason is increasing positive nuclear charge pulls the outer shell electrons closely with more strength. And that is how you see this. So it's pretty straightforward. No, not a difficult thing to understand. Okay, so that's the first trend that we see, that across the period, if you go towards the right, atomic size or atomic radius decreases. That's the first pattern that we have. It has a pretty straightforward value. Like the radius usually goes like this. If I were to graph, then I will see a very neat curve like this. That's how the size decreases. So on this side, I have the protons, and on this side, I have the size, the radius in nanometers maybe. So you will see it decrease. Pretty straightforward. Now, here's a table that I really like. We can find other patterns here, and we will try to answer where do these patterns come from. So if you look at this table, then you can see a few things about them, seemingly unrelated to each other. So sodium, magnesium, aluminum, the first three metallic lattice, the next three molecular lattice, not really lattice, molecular substances, except for argon. Argon does not have molecules. So first three metallic lattice, they're all losing electrons. Next three, all sharing electrons. And silicon in the middle, just like carbon macromolecules. It's in the group 4. Sodium plus sign, magnesium plus 2, aluminum plus 3. Group numbers match. Silicon atoms just sharing electrons, 4 each. And then do you notice this? P4S8 Cl2. And that is something you need to remember. Phosphorus is P4 from now, sulfur is sulfur 8 from now, and chlorine is obviously chlorine Cl2. These three are molecular, they have low melting point. The metals, they have high melting point except for sodium, which is in group 1, and we know from grade 9 that they have low melting point. And the melting points go like this. The melting points are increasing from magnesium to aluminum, but they're not that increasing, like they're very close to each other. Silicon is really, really high. And then we suddenly have a rapidly decreasing low melting point, like really, really low. Chlorine is -101, argon is -189. Doesn't look like a pattern, right? To be honest. 44, 119, -101. Koi pattern nazar nahi aa raha hai. And then electrical conductivity for metals, it's high. For non-metals, it's low. For silicon, it's moderate. Wait a minute. Why? We don't have any free electrons. It doesn't look like it. Sure, metals have free electrons. There are questions that might come to your mind, and we already know the answers to that. We know that sodium has low melting point because the metallic lattice is weak. We know that metals conduct electricity because they have free electrons. We know that they have high melting point because the lattice is strong and the positive ions are attracting the negative electrons rapidly. There are some questions that might come to your mind which you might have to think about it, but you already know the answer. Like, why does S8 have higher melting point than P4? And the answer is really simple. It is the same answer that we give to each other when we talk about halogens. Down the group, melting point increases. Why? Because the electrons in the cloud increase. The number of electrons increases. So the London dispersion forces that they form, they're becoming stronger and stronger with more electrons. So phosphorus 4 atoms joined together in one molecule, compared to sulfur 8 atoms joined together with in one molecule. So obviously there's more electrons in sulfur 8 molecule compared to P4. So no wonder it has more electrons, stronger London dispersion forces, because stronger dipoles with it. So that's why sulfur 8 has higher melting point or melting point than P4. That's a pretty straightforward question. We already know the answer to that. But there are questions that don't really make sense right away if you look at it. Like, how come silicon is able to conduct electricity? Or why is silicon the one making micromolecule? Or why is it that sodium is the one with low melting point, but suddenly magnesium has high melting point? Why is that? So there are a few things that let's try to talk about melting point. Now, there will be many points here. I'm not sure whether I can write all of that, but so the first three, electrons are lost. There is delocalized electrons, so cations, and obviously the size is decreasing. Aluminium is smaller size than sodium, so charge density of aluminium is much stronger. So bonding is stronger and melting point is stronger. So what words did I say? I use the word delocalized electrons. I use the word charge density of cation, because there are only two things that determine how strong the force is going to be. It's the strength of charges, the size of the charge, and how closely they are packed. How big is the ion or electron or whatever you're talking about? How big is the area in which these charges are moving around? So aluminum has a much higher charge density than magnesium. So no wonder aluminum or magnesium, both of them have higher melting point than sodium. Sodium doesn't really have that high charge density. The electrons that it gives away are just one electron for every one atom. Okay, why is silicon abnormally high? Because it has a giant covalent structure. So if you want to melt silicon solid and convert it to silicon liquid, you will have to break all the covalent bonds in the giant structure. And that will require more energy. No wonder it has very high melting point. Why does S8 and P4 and Cl2 have low melting point? Because they have simple molecular structures. There's van der Waals force there. There's London dispersion force there. Okay. Why is S8 greater than P4? And why is P4 greater than Cl2? And why is Cl2 greater than Ar? All of those answers come from the number of electrons. The ones with lower number of electrons in the atom or molecule have lower melting and boiling point. So the greater the charge, the greater the strength of dipoles that form, greater the melting point. There you go. Makes sense. Melting point, any confusions? Are you able to explain why melting point goes the way it is for every individual one? Are you able to do that?
Sir, can you explain it again?
For which ones?
For phosphorus, again.
Okay, so phosphorus, sulfur, chlorine, and argon, all four of them have London dispersion forces in them. Okay, the first three are molecular, argon is atomic, but all of them will have London dispersion forces between them when they're solids. London dispersion forces come from dipoles that are really created. The strength of the dipole comes from how many electrons are involved in the cloud. Sulfur 8 has the greatest number of electrons here. So that's why the dipole created is the strongest amongst these four. That's why it has the highest of the four melting points. Argon has the lowest number of electrons in the argon's cloud has less electrons. The dipole created is weak and it has the weakest or lowest melting point. All right, the next pattern that I want to talk about is electrical conductivity, because that is pretty insane for something like silicon. Like, क्यों ये conduct कर रहा है भाई? Like we understand it for sodium, magnesium, aluminum. They have more electrons that they're going to delocalize. So obviously they're free to move around. They are going to conduct electricity. Sodium has less, magnesium has more, aluminum has even more. So the conduction is high. There are electrons moving around. But how come silicon is able to do that? So silicon, we have to remember, silicon is a semiconductor. What is a semiconductor? Semiconductor is something that loses a few electrons for every few atoms. Every atom might not lose electrons, but some of them might. And the more you dope it, doping is a term used for impure silicon or the impurities that you add to it. The impurities that you add will make that effect that it has. It's a semiconductor, it loses a few electrons. Every few atoms are going to lose a few electrons. How many depends on what it is mixed with. On its own, it will lose a few. It's a semiconductor. It's going to lose a few electrons, they will conduct. If you mix it with something like, I don't know, arsenic or germanium, it is possible that it will lose more electrons. They will make it more low, lose more, which means it will conduct more. And that is something we work with. And there are billion-dollar companies working on that. Intel, there is this Taiwan Semiconductor Manufacturing, TSMI, I think. There's this another company, a fruit company, Apple. They do this all the time. They try to figure out the best material they can to dope it and to make better and better conductors that will conduct and yet lose less energy while doing that. And that's how you get this whole computer industry going on. That's silicon. So the moderate conductivity is a manifestation of silicon's semiconductor nature. The next three, they're not conducting at all, and it's low basically means they're not conducting. And why is that? That is because they don't have any free delocalized electrons, no free electrons, no delocalized electrons. So there's nothing to carry the charge that you have. Unless you break the atoms, they're not going to conduct electricity. And yeah, that's it. Physical properties of these things. All right, so you need to know why the electrical conductivity goes like this. Why does it increase? Like from sodium, magnesium, aluminum, why are they conducting? They're becoming better and better conductors. Then suddenly there's a drop. Silicon is not that good of a conductor. And then absolute silence, no conduction whatsoever. You need to answer, you need to know the answer to that. Then melting points, again, why is it decreasing like that? Okay, so you need to know, you need to be able to explain this pattern and obviously the radius of the ion or the atom that you have. Now here's the interesting bit. This is the value for radius of ions that they make. Now again, my question is, why is the value for argon not given? Why is the value of argon's ion not given?
Because it doesn't form ions.
Because it doesn't form ions. Exactly. Next, we have these sodium, magnesium, aluminum. Do you see a pattern? Do you see a pattern in them? Like even silicon. The first four, are the values increasing or decreasing?
Decreasing.
They're decreasing. There's a decrease in the size that they have. And then there is a sudden increase for phosphide, and then that's decreasing as well. But which ones didn't decrease? There is a stark difference in the size. If I were to graph them, I'll probably get a graph like this. Like on this side, I have the elements, the proton number, and on this side, I have the size, the radius. Why is this the way it is? Why is this sudden increase over here? And then why are they decreasing like that? What's happening here? They're losing the last shell. They've lost a full shell. That's how they become positive ions. So radius is going to decrease from the atom. Atom is going to be bigger. The cation is going to be smaller. We know this. We know that cation is smaller than the same elements atom, and atom is smaller than same elements anion. That's usually what happens. Why is that? Because sodium, magnesium, aluminum, silicon, all of them have lost the last shell. But then not only have they lost the shell, they are also getting a positive charge, and the charge is increasing. Okay. The cation is getting smaller and smaller. Why is that? That is because Sure, it is smaller than atom. Why is cation smaller than atom? Because there is no shielding. There's less shielding, in fact, compared to the atom. Okay, they have lost a whole shell, so there is less shielding. Atom is bigger, cation is smaller. समझ आ गई? But why is it कि sodium बड़ा है और magnesium ion छोटा है और aluminium ion उससे भी छोटा है? That is because if you go from left to right, effective nuclear charge is also increasing. So now, even though all of them have two shells, they're pulling on it much strongly if they have more protons. So silicon has the greatest number of protons. It pulls the second shell strongest, which means the ion is going to be much smaller. Sodium isn't able to pull it that strongly, so the ion is bigger. By the way, notice that they all have 10 protons. Oh, sorry, 10 electrons, all of them. But those same 10 electrons being pulled by 11 protons in sodium compared to 14 electrons in silicon. Fark to padega. So the shell that you have, the last shell, it's even more closer to the nucleus because you have more atomic number. आगे समझ आगे कि नहीं
Sir,
आई?
I don't understand this. Please फिर से समझाते हैं.
दोबारा से देख लेते हैं. सोडियम के स्ट्रक्चर को देखते हैं. 11 protons, 12 protons, 13 protons, 14 protons. Electrons just 10. Shells structure is this: 2 8 2 8 2 8 2 8. Imagine 8, the second shell being pulled by sodium ion, 11 protons, compared to that same shell being pulled by 14 of silicon. कौन ज़्यादा strongly pull करेगा? Silicon. There's the nucleus in there. This is the first shell. और ये उसके और ये second shell है. So यहाँ पे क्या होगा? Obviously there is the repulsion coming from this one. This is shielding, and there is attraction towards the nucleus here. So this attraction is not that strong in sodium compared to silicon. Silicon is going to have a much stronger attraction. So no wonder this last shell is going to come a little bit closer to the nucleus compared to that for sodium. Sodium में यही थोड़ा सा बड़ा होगा. That same last shell is going to be closer for silicon compared to sodium because sodium is pulling with 11 protons, silicon is pulling with 14 protons. So छोटा हो जाएगा. Cation radius decreases if you have greater positive charge in the nucleus. Obviously, they're all isoelectronic. That is a term. They're isoelectronic because they all have the same number of electrons. But even if they're all isoelectronic, does not mean they'll have the same shells, or they will have the same size. Something with greater protons will be smaller, something with lesser protons will be bigger. Okay, let's talk about the negative ion. Negative ion we know is bigger than the atom. Why? Because you're adding more electrons. Those electrons involve or increase the shielding. They're being repelled more by the already present electrons. Remember shielding? Shielding is when the electrons that are already there push the outer electrons. So you're adding more electrons, they're going to be pushed away. So in the negative ions, you have 15, 16, 17, 18 protons, and you suddenly have 18 electrons in all of them because they all gained more electrons. This is phosphorus with -3, this is sulfur with -2, chlorine with -1, and argon. Argon is 18 naturally. So we would expect that the shielding will be higher in phosphorus. Why? Again, where is the shielding coming from? So the nucleus is in the center. There's the first shell. I'm not drawing the electrons. Second shell, and then the third shell. This third shell is being repelled by the electrons inside. So the first shell is pushing the electrons on the second shell, that is pushing on the electrons on the third shell. And nucleus is pulling back on them. Nucleus is trying to pull them back. The size is determined by which force wins, the repulsive one or the attractive one. Now the thing is, in phosphorus, in sulfur, in chlorine, the ions, all of them have the same number of electrons. All shells are complete, 2 8 8, that's the structure. But in phosphorus, 15 electrons are pulling on the last. In chloride, 17 electrons are pulling on the last one, 17 protons totally. So which proton wins? The chloride ones. Chloride is able to pull on the same last shell more than phosphide. Same reason as positive ions. Turns out from left to right, positive charge increases, So the attraction towards the nucleus increases from left to right. From left to right, we would expect ions to be smaller. That's a general pattern. Cations, they're becoming smaller and smaller and smaller. But there's a big jump here. Where is this jump coming from? You have added another shell. That is why there's a jump. If you had two shells, the pattern remains. You're getting smaller and smaller and smaller. And then suddenly you have added a shell. And you add a shell after the 14th group. Why? Because you start becoming negative ions. So this will be much easier to visualize if instead of looking at atoms or ions in the same period, we were looking at ions across different periods. So for example, if I were to zoom out a little bit and draw or try to figure out the ions from carbon onwards. So carbon, this is nitrogen, N3 minus. Then there's oxygen, O2 minus. Then there is fluorine, F minus. Then there is neon, then sodium +1, magnesium +2, aluminum +3, and silicon +4. Now, all of them are isoelectronic. They all have 10 electrons. 2, 8, 2 shells in all of them. What pattern will you see in the size? They're not in the same period even, but they're showing the same trend because their structures are the same. Same 2 shells being pulled by 7 protons in nitrogen, being pulled by 14 in silicon. Look at how large the difference in atomic size is. Kyun na ho? You are getting more protons pulling on the same shell. For the anions on the left side, these anions, the size decreases because greater nuclear attraction, but the same number of shells. Okay, so there's more shielding here, more shielding, because आजा के बाद तो यही है ना, there's the shielding from inner shells and attraction of the nucleus. In nitride ion, you have shielding from the first shell, which is being countered by attraction from just 7 protons. But in silicon +4, you have same 2 shells, same shielding, but attraction by 14 protons. No wonder silicon +4 is much, much smaller than nitride. And the pattern goes like that. Things are much easier if you try to just look at 2 forces. Repulsion from inner electrons, which is shielding, attraction from the protons, and then figure out what will the pattern be. If you keep on adding more protons, but don't change the shielding, size will decrease, right? And that's what we see here. But what will happen after silicon? There will be a big jump. There will be a big jump. Why? Because after silicon, you're getting phosphide. Phosphide? And phosphide does not have 2,8. Phosphide has 2,8,8. You have added a shell. So obviously the atom is going to be much bigger. The ion is going to be much bigger. And after this, it's going to follow the same pattern again. So the pattern of ionic size is this. You break it down. So this is the size of all isoelectronic, and this is the pattern that you'll see. But if you try to, instead of breaking it down like that, you break it down like this, like from one shell to the next, you will see a pattern that goes like this. But within the same isoelectronic structures, it is always going to fall. And why is it going to fall? Because you're adding more protons with same shielding. So anions are bigger than atoms because they have more shielding. Cations are smaller than atoms because they have lost an electron shell, which means there is absolutely little, very little amount of shielding left. Okay. Why are the ions, the anion towards the middle bigger? Because they have more shielding and less strength of attraction. And why are the anions towards that are closer to noble gases more like smaller, like chloride, bromide, iodide? Why are they smallest anions in their whole period? Because they have the greatest number of protons but lower shielding. Same shielding. Get it? So from nitride to silicon in the periodic table आप लोगों के सामने होना चाहिए इस वक्त. From nitride to silicon, there is going to be a constant decrease in atomic ionic size, because you are going to get ions of the same electrons, isoelectronic ions, but with increasing proton numbers.
Yes, sir.
Yes, sir.
Perfect, perfect. We have already talked about the ionization energies. I think we talked about that when we talked about ionization energy, when we studied that. Ionization energy was this. The pattern was this. Usually, this is the general pattern. What's happening here? 1s1, this is the s1, this is s2, p1, p2, p3, p4, p5, p6. Okay, why is the energy decreasing, ionization energy decreasing from s2 to p1? It's decreasing because of more shielding from the s orbital. Okay, why is the energy decreasing from p3 to p4? Because there is mutual pair repulsion. The words are important. So this falls because of mutual pair repulsion. Thank you. This falls because there is shielding from s orbital. And overall it increases. Overall, the general trend is that increases. Why? Because more protons say similar shielding. Why similar shielding? Because there is the same shell that they have. And यही तीन बातें वो एग्जाम में पूछ लेता है. What is the general trend? Explain it. The general trend is ionization energy increases because as you go from left to right, protons are increasing, shielding remains virtually the same. Okay, why is there a fall from magnesium to aluminium? No problem. From magnesium to aluminium, there is going to be an increased shielding from s orbital. It all boils down to just two forces: the repulsion of electrons, which is shielding, and the attraction of protons. That's it. इतना आसान है पूरे एटम्स को समझना. प्रोटॉन, इलेक्ट्रॉन, बस, और कुछ है नहीं. Okay. Why is there a fall from P3 to P4? Like, why is there a fall from what is P3? P3 is nitrogen, right? Yeah. So why is there a fall from nitrogen to oxygen? Because there is mutual pair repulsion in oxygen. Force electron P में चले जाता है. Okay. You can do the same thing with the period 3. In period 3, I think you have phosphorus and sulfur. So why is there a fall from phosphorus to sulfur? Same reason. That is the idea of trends in the periodic table. Now, of course, they are not all the trends. आज हमने सिर्फ elements के trends को देखा है. Tomorrow we'll talk about trends of the reactions and trends of their compounds, and they are even more interesting and as easy to explain as these. In all of them, you have seen the only two things that matter are protons more and are they winning? So things become smaller. Are electrons winning because the shielding increases? Bus. Tomorrow we'll talk about their structures and why they do that, like what happens to chlorides or what happens to oxides. Are they amphoteric? Are they acidic? Do they react? Do they not? That's what we're going to do tomorrow.